Hi, it's Dr. Harris, and we're in the middle of Chapter 5 in our Statistics Math 111 video series, and we're taking a bit of a break from slideshow 1 to look at uh, not so much a tutorial as I've written here, but an activity that will allow us to uh, get a sense of what the sampling distribution of a sample proportion might look like. So let's look at the scenario, the question that we're going to be using our R code to analyze. Suppose we've got a large city. We'll say that there are 200,000 adults in this city, and uh, we want to have an idea of what percentage, what proportion of those adults are supportive of a plan to build a new high school in the city. And suppose that unknown to us that the actual percentage of adults that approve of this plan is 70%. So that's a true statement, but the people who are interested in finding out what the actual percentage is won't know that. And so what the planners, the people who are trying to figure out what the level of support is, can do is they can take a random sample of adults from the population of the city and ask them the question and see what proportion of the sample is in favor of the plan. And so we're going to uh, look at the output of a number of scenarios where we have different size samples to get a sense of what happens with the distribution of the sample proportion if we were to essentially repeat the process of conducting these polls over and over and over again. So jumping right into the code, I'm not going to take a lot of time to analyze much of it, but maybe you can follow along a little bit. What we're doing is we're assigning 200,000 to the variable pop underscore size. 0.7 is going to be assigned the value of true underscore proportion. And then the next line, possible entries, basically just assigns 70% of the 200,000 entries to supporting the plan and the other 30% to not supporting the plan. And initially, we're going to set our sample size to 100. So sample size is the variable that records the number of individuals in our sample. Okay, the next chunk of code here actually takes a single sample of size 100 and computes the percentage of that sample that was chosen that supported the plan, that had the value support attached to them. And in this particular example, we don't see the 100 individuals that were sampled, but apparently 65 of those 100, or 65%, the proportion 0.65, were the number of supporters that were in that sample. Or 0.65 was the proportion, 65 out of 100 was the number of supporters. Let's repeat this just to see that we actually get different values for different samples chosen. I've done it 2 more times, and it turned out that the second time I chose a sample, 75 of them were supporters, and so the sample proportion in that case was 0.75. And the third time, when I chose 100 individuals, I got 64, or 0.64 as my sample proportion. So I'm trying to convince you, or at least make plausible to you, that the value of the sample proportion depends on the sample chosen, and the sample chosen will vary from random sample to random sample. So we would expect to get different values for p hat for different samples. So the question becomes, if I did this sort of process over and over and over again, thousands and thousands of times, and then collect it into a graphic, a bar graph, a density plot like thing, uh, what would that look like? So the next uh, bit of code that we're going to look at is going to try to answer that question. So we're going to actually take 10,000 samples over of size 100. So we're using sample size equal to 100 still. And what this code does is it computes each of those 10,000 sample proportions. So it's basically constructing a list of 10,000 sample proportions. And then on the next slide, the command gf_bar is going to create a bar graph out of that. And it'll resemble a density plot, the things that we've seen earlier in the course. And so here is our approximate density plot, bar graph, for the distribution of p hat for this population. So we notice a few things. We can describe its shape. We can describe where it's centered. We can describe approximately what we think the standard deviation might be. So we're going to be looking at that in our next in a couple slides from now. But just to show you, if I just go back real briefly, I set a random seed here. I took value 214. What that does is if I use the same number in this spot, each time I would get the same set of samples. Each time I would get a different density plot. And so what this does is it allows me to generate a different set of random samples each time. And so I'm going to perform this again with a different seed. I'm going to use seed 457 rather than seed 214. But I'm running the exact same code except for the place where I'm starting to draw my random numbers from via the computer. And so I'm going to get a different set of 10,000 samples. I'll get a different set of sample proportions. Let's take a look at what that distribution looks like. Well, it looks pretty similar. So go back. This was the first set of 10,000 sample proportions written in bar graph, represented in bar graph form. And here's my second. They're not exactly the same, but they have a number of similarities. And so let's think about this. There's some questions on the next slide that I want us to be thinking about for just a couple minutes before we go to the answers. What can we say about the shape of the distribution? We've seen two examples of approximations of the sampling distribution for p hat in this particular case. What can we seem to say about its shape? What can we say about the center, the mean of that distribution? And what can we say of what might we approximate the standard deviation as? So I'll come back here for a second, let you look at this, and then in the slide after the one we just saw, I'll attempt to answer those questions. So you may want to stop the video for just a minute, think about what the answer to these questions might be: shape, center, spread. So let's give you a second to think. And let's go and look at the answers now. Hopefully you've thought, well, this is a bell-shaped curve. And we might even say that it has a normal distribution based on things we've seen earlier in the course. Where did it seem to be centered? Well, if we look at both of these, center of the distribution seems to be pretty close to 0.7, which, if you recall, was the value of our population proportion. So it looked like it's bell-shaped, possibly normal, centered at the population proportion value. And then finally, standard deviation, remember that according to the 68-95 rule, about 99.7% of all observations from a normal distribution live within 3 standard deviations of the center. And so we can come back here and think about, well, how far is 3 standard deviations? If the center is at 0.7, it looks like we get out about as far as 0.85 out here, about 0.65 down here. And so it looks like all the action, almost all the observations are going to be between 0.55 and 0.85. This is 0.55 down here. So almost all the observations are between 0.55 and 0.85. So 3 standard deviations would be the distance from the center to one of those edges. And so 3 standard deviations would be the distance from 0.7 to 0.85. And so that's going to be 0.15 is about the distance from the center to capture almost all the observations. So if 3 standard deviations is 0.15, that would make a single standard deviation to be 0.15 divided by 3, or 0.05. So we're going to estimate the standard deviation to be about 0.05, about 5 percentage points. Okay, so we've got an idea of shape, bell shape / normal, center, 0.7, the population proportion, and in this, for the sample size 100, it looked like the standard deviation was about 0.05. What I want to do now is I want to look at different sample sizes and see what stays the same and what changes. So we're going to increase the sample size now. We're going to look at 3 other cases, 200, 400, and 900 for our sample sizes. And we wanted to see what happens, what stays the same, what changes. So the only difference from what I'm doing before is I'm setting a different seed and I'm changing the sample size. So here I'm going to make the sample size 200. I'm going to draw 10,000 samples and I'm going to compute the sample proportion for all of those 10,000 samples. This is what I got for my approximation of the sampling distribution when my sample size is 200. What does it look like? Well, it's still fairly bell-shaped. We might think it's normal. It's still pretty close to centered at 0.7, but this time it looks like almost all the observations are, say, between 0.6 and 0.8. The previous case, we went out from about 0.55 to 0.85, so we're more tightly packed here. Our values seem to be almost between 60% and 80% this time with a sample size of 200. So the distribution is less spread out. Things that were the same, the shape was still bell-shaped. The mean still seemed to be at the population proportion, but our standard deviation went down. And so if almost all our observations are between 0.6 and 0.8, the difference between 0.7 and 0.8 is 0.1. That would be 3 standard deviations roughly. So 1 standard deviation would be 1/3 of that, or about 0.033. What if I do 400? So again, all I'm doing is I'm changing the sample size to 400. I'm using a different seed. And here's what the distribution looked like. Still pretty bell-shaped, still pretty centered, right around 0.7. But this time our observations seem to be more or less between maybe 0.625 and 0.775. And so now that would mean that 3 standard deviations is about 0.075. And so I divide that by 3 to get 1 standard deviation. It's about 0.025. And finally, if I change the sample size to 900, again, I'll use a different random seed. Our distribution of the values of p hat looks like this. Again, very bell-shaped, very centered, right at 0.7. It's not on the axis this time, but 0.7 is right here. It looks like things are pretty centered around that. And this time I would say that most of our observations are going to be, say, between 0.65 and 0.75, roughly speaking. So about 0.65 to 0.75. That means our standard deviation, that 3 standard deviations would be about 5 percentage points. And so 1/3 of that is 0.0167 approximately, rounded. And that's going to be our approximate standard deviation. So here's a table that summarizes what we've seen from this exploration. As the sample size changes, the shape doesn't change, the center doesn't change, but the standard deviation seems to be going down. And this is going to be our starting point in our next slideshow, our continuation of slideshow 1.